The first one is entitled Behavior Composition as a Fully Observable Non-Deterministic Planning. It will be presented by Miquel Ramirez.
Yep. Good afternoon, everyone. My name is Miquel Ramirez, and I'm going to present this joint work with Nitin Yadav and Sebastian Sardina at MIT University in Australia. This work is about compiling a control problem called behavior composition and developed by Giuseppe Di Giacomo, Fabio Patrizzi, Sebastian Sardina, and many other people over the years, where basically we have we are looking for a controller that activates devices upon request from a third party, which is not explicitly represented, but is generating this kind of events that need to be satisfied in some way. On the other hand, non-deterministic planning, there we want a plan, a policy, conditional plan that selects actions every time step, so to reach the goal or that. Behavior composition sounds like a problem which is close to that of planning, but it's a bit different in some respects. For instance, typical behavior composition instance comprises a system of devices, in this example 3 cameras, right? Of those devices, we have an operational model which basically describes which are the capabilities and characteristics of these devices. In the example of the 3 cameras, we have 2 cameras that can only point to one single location, X or Y, and we have another camera which can point to either direction. But the cameras that have, less degrees of freedom never crash when trying to take a picture, while the camera which it's able to move more freely sometimes crashes, right? And what we want to compute is a controller that is able to handle sequences of requests where first it is requested that some camera is pointed at a certain location, and then to take a picture of that location with that camera. So what are the differences? First, in planning, it's a problem of reachability, of determining if there exists a plan that guarantees reaching certain condition. In behavior composition, what we want the controllers is to be always able to handle this kind of requests without crashing the system. On the other hand, we have another difference is that in behavior composition, the controllers are mapping system traces, which may be infinite, into device activations, and in planning, we are just considering finite states. But we'll see that the second difference is easy to breach, the first one is not so easy to breach. So the goals of this work is to bridge this gap between safety and reachability, and here we basically take advantage of the very nice work by Fabio Patrizzi, Nir Lipovetsky, Hector Gevner, and Giuseppe Di Giacomo in ICAPS 2011. And then, using their contribution, we define a translation of behavior composition into fully observable non-deterministic planning. We show, with a theorem, the excellent correspondence between controllers for behavior composition and plans for non-deterministic planning. And we finally want to evaluate the performance of the state-of-the-art in non-deterministic planning to see how good as a computational framework is planning for this particular problem. So, first I will give a very short overview of behavior composition and fully observable non-deterministic planning, and then I will go over the first contribution, which is the mapping, and then the experimental evaluation. So, behavior composition problem consists of a system, which is a set of behaviors. These behaviors, as I said, are operational models of devices which are characterized as transition systems, automatons, which are defined in terms of a set of finite states, a set of actions, a transition function, which may be non-deterministic, and an initial state. And then we have a target behavior, which is something which is not readily available, but we think that can be built using the behaviors we have already in the system, which is defined as well as a transition system, and has a set of actions which we know some of all of the behaviors in the system are able to comply with. A history of the system is just a possible trace of the synchronous product of this system, which really means that the behaviors, the automatons in the system are allowed to evolve. When the whole system evolves, some of the behaviors can remain in the same state, and others, which is the one that is actually honoring the user request, can evolve to the state that prescribed by the transition relation. HS is the set of all possible histories of this system, and a controller needs to be able to select behaviors for any of these possible traces. So, for instance, for the example, the problem I was describing at the beginning, a target behavior will look like that. We will have an automaton with 3 states. Each of these states is actually referring to a world state, which in this work we decided just to sort of hide the representation of the environment under these labels, right, the names of the states. So the first state is state idle, where nothing has been requested. As soon as we get a request, we either get a request for having a camera pointing to X, and then we go to state T1, or we have a request to point the camera to location Y, and we go to the state T2. And then the only possible, according to the specification of the target behavior, is to take a picture of that location, which takes us back to the idle state. This automaton only advances when actions are requested. And that's a bit different from planning, because in planning it's actually, we have an agent which is trying to achieve a goal, right? And here it's more like things are happening and our agent is trying to react to those things in a manner that at any point we can guarantee that we will be able to honor the request being made. The behaviors, so the system of the example, will look like that, where we have 3 automatons. 2 of them are very simple, with 2 states, standby and ready to take the picture to a particular location. And then we have the other one, which is more fancy, right, that allows us to ready the camera on 2 different locations. But as you can see, it has a non-deterministic transition. Whenever it executes the action take picture, it could happen that it goes back to the standby state or goes into that crashed state, basically effectively killing that part of the system, right? I said these automatons can evolve independently. So, for instance, we can say that C3 executes the action point at Y and then take picture, and the others can remain in whatever state they started, right? But they are always synchronous with the target. When the target makes a transition, at least one of the system also has to make a transition. But, could be any of the behaviors in the system. So a controller basically is a function which is mapping the set, an element, one trace, and one action, which is the action being requested, to one of the available behaviors, right? And we say that a controller realizes a trace of the target behavior if at every time step and for every action being requested by the target, there exists at least one behavior able to execute that action. And we say that a controller fully realizes a target T if the controller realizes, is wanted to realize, all the traces possible in this system. Planning, it's the formulation we are using, basically we use the same formulation, the formulation proposed by Olivier Buffet and Blake Bonnet in 2006 for the competition, where we have a set of fluents, which we use to describe the states, initial state, which is a full assignment of a set of fluents, and a conjunctive goal formula. The actions are a bit different from classical planning in that they can allow deterministic effects, as we all know, or non-deterministic effects, which are denominated one-off effects, which we use this weird notation to denote that whenever you do the action, at least one, well, exactly one of these of the effects listed will be happening. And something that I find is quite nice is that we can also have conditional effects as a one-off effect. So it's quite expressive. It's really simple and it's quite expressive. The solutions for this planning task are policies or conditional plans that map states into actions. The interesting thing is the solutions of fully observable non-deterministic planning come in 3 flavors, depending on the kind of guarantee they give us on reaching the goal. We have weak plans, which are plans that when they're executed, they guarantee that we'll be achieving the goal sometimes, sometimes they don't. Strong, which are plans that always are guaranteed to always reach the goal and will never visit the same state twice. And strong cyclic plans, which guarantee reaching goals and allow for loops during the execution. Some of the audience may be wondering, well, this is very much like the notion of policy in MDP, and it is. I mean, fully observable and non-deterministic planning in MDP is pretty much the same thing. The only thing is that in non-deterministic planning, we don't have a model of probabilities, right? The most interesting, well, from my point of view, class of solutions is the strong cyclic solutions, where we are assuming that all the action outcomes are fair. That means that this basically means that all the outcomes of an action can happen. It's not like we have an adversary that it's selecting things just to make our life more difficult. So we know that if we get into a loop, eventually, I mean, which may take an infinite number of steps, but eventually we will be able to exit that loop and get to the goal. And the key idea of our paper is that the controllers for the behavior composition problem fit into strong cyclic plans, because the target can have any number of internal loops. I mean, for instance, the target can keep requesting the same action again and again, and we also assume fairness in this request. I mean, we assume that the request, if they are described into the description of the target, they will be made at some point. So I mean, in here, the loop we have, I mean, since this becomes a non-deterministic problem, right? We have a loop which starts at T0 and ends up at T0, but its body is basically a conditional, right? If we get requested one kind of action, then we will go through one branch of one possible execution of this non-determined conditional plan, and if we get a request for another action, we'll go through another branch of this conditional plan. So the basic idea, we take the description of the behavior composition problem and we encode it into fluents, actions, initial states, and goals. This is performed in two steps. The first step, we define a planning domain. That means a set of fluents, an item state, and an action, which models the dynamics of the behavior composition problem. And then, in order to account for the infinite rules, we defined a planning task using Patrizzi's work in ICAPS to define, as we'll see, I mean, a set of auxiliary fluents, which allows us to prove that we are actually reaching in a one linear execution a state which is equivalent to the state we started to execute the body of the loop. So the configuration of the target and the system is encoded as a set of fluents, where we have fluents denoting the current state of the target, fluents for denoting the current state of each of the behaviors, a fluent for denoting which is the action which has been requested by our target module, another fluent to signal whether that action has been delegated, I mean, has been executed by some behavior, and another flag which allows us to model the state of being ready to generate a request. So the initial state of the planning domain is that the target is ready to generate a request, it's in its initial state, and all the behaviors are also in the initial states. Then the dynamics of the behavior composition are broken down into three different planning actions. We have kinds of planning actions. We have generate actions, one for each state of the target, which basically choose non-deterministically which is the action which is going to be requested by the target module. Then we have delegate actions, one for each action which is supported in behavior, which basically make the bookkeeping of sort of simulating the execution of the action and having the behavior evolve to whatever state is prescribed by the transition function, and a progress action, which basically does the bookkeeping of putting the target in the state ready to generate another request. The infinite rules, we account for that by adding a set of auxiliary fluents, which basically mirror the fluents we already have defined to capture the configuration of the behavior composition problem, and two additional actions. A loop action, which allows us to guess the start of the loop and sets these auxiliary fluents to whatever are the truth values of of the state variables, and an end action that verifies that the state recorded in this auxiliary fluence is satisfied. So in such a way that we rule out empty loops, and doing this end action in a state which doesn't match the start of the loop that we guessed results in a dead end. And the goal is true, I mean, it's made true only by the end action, which basically means that the goal is only reached if we can make sure that we are actually at a state that allows us to restart the loop from the beginning. With this encoding, we can show that there exists a controller if and only if exists a strong cyclic plan for the planning task resulting from our compilation. The idea of the proof is very simple. Basically, we can show a mapping between non-overlapping finite subsequences of the history of the system, and the two gaps we had between behavior composition and planning, the one regarding controllers using full histories, well, it was shown that memory-less controllers, like a conditional plan, are sufficient for this problem. And this is available in a recently published journal paper. And this formulation, the word it has is that doesn't account for traces and for targets with finite traces. Yet, we think it's quite easy to do just by adding a no-op action and add this no-op action to our very trivial behavior that can always be delegated, can get down this no-op action. Let's see. So, well, we did our translation, we showed the correspondence, and the thing is, well, can we compute these, I mean, solutions for the behavior composition problem with planners, and how well they do? So, since this problem doesn't have any practical implementation yet, actually the idea is that this work should convince someone that it actually can become an actual implementation in the real world. We came up with 5 different benchmarks where we had 3 different kinds of behaviors, like very simple behaviors, one single state, behaviors which were non-deterministic and basically are modeling, like, say, this is taking into account chip modeling as saying everything is in one single state, and then we have a state to denote that we have crashed, and then we have more fancy behaviors with several states and several actions that interlock and are more like puzzle-like. And regarding targets, we consider 2 different types of targets. One, which we have linear sequences, linear loops, many of them, and only one branching point, and another where these possible sequences keep branching in a tree-like fashion. So what we were expecting to see was to be able to measure the impact of non-deterministic behaviors, because it seems to be a problem for model checkers, which has been used to solve this problem as well, and the rate of growth in the number of traces. If we have many traces, that means that when the non-deterministic planner is trying to prove that it exists a strong cyclic plan, there should be a harder search problem. And as per suggestion of Sebastian, I mean, we wanted also to consider these behaviors with many states and actions, which, I mean, they were hypothesized to be difficult to coordinate because you need to keep jumping from behavior to behavior in order to get the target satisfied. So, in terms of software, we took off-the-shelf, no modifications, Chris Mui's policy repair planner, which was presented last year here in ICAPS, and is based on the fast downward planning framework. And its inputs is the behavior composition instances mapped into planning tasks, and also well-established verification frameworks, which some people know as model checkers. And the first one we used was Nougat, which basically is a two-player abstract game solver developed by the model checking group in Trento, which is based on USMB, which is a very well-known model checker, and Maximus, which is similar in the sense it's doing the same kind of logic inference. The only difference is that it's using a different kind of formulas to represent the set of states. I mean, in this case, OBDDs, and that makes quite a difference. And the input is behavior composition problems mapped into Safety game following the mapping given in the reference there. And we also fixed the resources for this computation just to 30 minutes and 2 gigabytes of RAM, which is not much, but I mean, for our purposes of just testing if it was feasible, I mean, was right enough. The results was that the benchmark fell off a split in 2 different groups. The first group involved this kind of behaviors, the simple ones, and with these behaviors we saw that both PRP and NuGet solved every problem in the benchmark, but Maximus did very poorly. That was a bit of a surprise because Maximus was supposed to be faster than NuGet. PRP was faster than NuGet when we had many behaviors, and we could see that curve very clearly, but PRP is much slower when, but PRP is much slower when we have these tree-like targets. One important thing when talking about times is that the model checkers do not produce the controller. They just tell us whether it exists or it doesn't, which basically means that there's some sort of constant factor deck which can be quite big in order to stack the controller, which we are not accounting for. And the second group involved these behaviors, which were the puzzle-like, where NuGet coverage was 50%, which was not bad, I would say, and PRP just did 20%. And the thing that was a bit, well, worrying, and it's about these behaviors in concrete, is that while the model checker timed out, the planner was exhausting memory really quickly, in some instances really quickly. In general, for this kind of behaviors, the weak plans were also harder to find, which also created problems for PRP. So wrapping up, what we have this work, it's quite concrete. We has 2 main legs. One, a mapping of this problem, behavior composition, into non-deterministic planning, and then an evaluation, which can be criticized, but I think it's quite extensive and tries to understand, or tries to produce data that allows us to understand what are the strong points of the available techniques when it comes to solve behavior composition. So, as a conclusion, and for your work, this was the first practical implementation of this idea of behavior composition. So, as happens when you make a practical implementation of anything, new questions arise, and we have several ideas on how to further extend behavior composition to make it more flexible and more interesting and probably harder to solve. And on the other hand, we also were quite surprised by the gap between the different approaches to fault, because originally we wanted to test with MVP, but MVP, we couldn't make it run in a modern computer. So we had to resort to use the model checkers, sort of doing by hand, to say so, the translation that MVP does from PDDL to the logical formulas. And we really look forward to identify, why model checkers are stronger in some cases, and, well, maybe we can do some contribution specifically to planning. And that's it.